Hello, everyone. If you could take your seats, we're going to begin in about a minute.
You will be live. If you start talking like a whisper, most people can hear you. So if you need to speak,
I need to behave.
yeah, you're live now.
Thank you.
Welcome back, everybody. I think we'll get started. So now in my theme of signaling, we're going to hone down and to the cellular level and hear about how cells communicate with each other and the ways that can go wrong and produce dysfunction. And then we're going to come back to our interpersonal signaling to hear inspiring stories about how we can work with cellular dysfunction when we have person-to-person function. So it's a pleasure to welcome
Thank you
Dr.
very much.
Roland.
I was going to start by thanking Larry for inviting me, but I'm not going to do that. Because after the stellar scientific presentation this morning, and then the fantastic talks we just had on matters much more important than what I'm going to talk about, I feel like a very pedestrian lecturer. So I may thank you if I feel good after. Okay. All right. So that's the title of my presentation. There is a tradition in the medical world that you always present your disclosures, and usually you don't let people read what it says. So because I realize that this meeting is not a bone expert meeting, I decided to start with Bone 101, a few slides to tell you or remind you for some what we are going to talk about. So bone, as you can see here, first of all, is beautiful. But besides being beautiful, it is a structure that is mineralized, and that, as you can see here, is formed of two types of layers. The cortical bone, which is outside of your bone, that's what you see normally. And when you look inside, you have this very thin network of mineralized trabeculae, which we call trabecular bone. Now, if it was not a dry sample as before, but a fresh sample as shown here, you can see that all these small spaces within the bone itself are, of course, occupied by cells. And these cells constitute a very important organ as well, which is the hematopoietic bone marrow, the source of all the cells in your blood, all the immune system, among other things. So if we first zoom in an area, here the bone is black, stained in black. If we zoom in and look at what is inside the mineralized tissue, this is what we would see. And that is that you have a very large number of cells within the mineralized bone matrix that we call osteocytes. And they turn out to be the most abundant cells in bone in one of the largest organs of the body. That's a different way for you to think about your skeleton. We think a bone, another bone, but you have to look at it as an organ. And when you do that, you realize that it's a pretty large organ. So we are talking about a very large cell population here. And these cells reside within mineralized bone matrix. And therefore, they have some special features that you can see here. They have a large number of what we call dendrites, similar to what you would say about nerves. And as you can see, these dendrites constitute a network, a dense network, that permeates entirely the mineralized matrix. So that even when they are embedded deep within the tissue, they still have communication with the space of the bone marrow, actually. In fact, over the last 20 years or so, we've realized that these cells are extremely important. It would be surprising that you have so many cells that would not do anything. And actually, they are the cells that sense mechanical loading on the skeleton. They are cells that are capable of mobilizing calcium and phosphate from the bone itself, this for calcium and phosphate metabolism. And they are the source of a hormone, FGF23, which targets the kidney and regulates the excretion and absorption of phosphate. Of course, they are in a very good position to know what's going on with phosphate. And finally, they secrete two cytokines, one called rank ligand and the other called osteoprotegerine, that have opposite effects on the regulation of bone resorption. And we'll talk about that in a minute. So now, after looking inside the matrix, I would like to take you along the surface here of these mineralized bone pieces, that is at the interface with the hematopoietic bone marrow. And when you do that, you encounter actually three types of surfaces, and let's look at the first two now. The first type of surface shown here is a surface where bone is being formed at the time that you are looking at your tissue. And when a bone is being formed, it is secreted here as a matrix, mostly of collagen and non-collagenous proteins, that will take a certain time before it gets mineralized. And the cells that are responsible for this secretion of all this material are shown here. They are the osteoblasts that form bone. Notice in passing that you have here a young osteocyte. That is a cell that is now embedded within the matrix before it gets mineralized. And that reminds you that the osteocyte is actually originally an osteoblast that gets entrapped in the formation of matrix over time. Now, we can show the mineralization process by using fluorescent labels shown here at sites like that. And this is a very important technical aspect that allows us to measure the rate at which the tissue is turned over with time. The second type of cellular activity that you can find along the bone surface is shown here. This is a so-called osteoclast. It's a multinucleated giant cell that attaches to the bone surface. And when it attaches to the bone surface quite hermetically, it secretes under its belly, if you want, enzymes and protons. Actually, it acidifies this extracellular environment. And by doing that, what it is capable of doing is to resorb very efficiently the bone, the mineralized bone matrix. And this shows the seal that the cell is forming under its belly in order to secrete enzymes and acid within closed environments. So, of course, these three cell types communicate very closely with each other, and I am not going to describe all these connections that have been identified, but suffice it to say that it's mostly constituted of various cytokines, most of them with very short range actions. Now, as a matter of fact, this crosstalk between these three cell types leads to a coordinated action along bone surfaces, which we call the bone remodeling sequence. And just to describe it briefly here, if you start from inactive surfaces, the first event is an osteoclast and bone resorption. And what this cell does is to remove tissue that for some reason needs to be removed, either that it's too old tissue or that it needs to be adapted or that the body needs calcium and phosphate. And when this cell resorbs actively the mineralized bone matrix, it moves along the bone surface and leaves signals that recruit the repairing cells, the bone-forming osteoblasts. And in the end, when things go normally, you just have replaced a piece of bone by an equivalent but newer piece of tissue. The way I like to present that is to emphasize the fact that these activities are cyclic. And in a way, maybe the simplest way to describe that is to say that we are dealing with two cellular lineages. One is the hematopoietic lineage that leads to the formation of pre-osteoclast and osteoclast within the monocyte macrophage lineage of the marrow. And the other lineage is the mesenchymal stem cell lineage that leads to the formation of osteoblasts, osteocytes, and as we will see, also lining cells. So these two cell lineages have two opposite functions, and of course they need to talk to each other if you want to have a coordinated activity. In our jargon, the fact that osteoclasts can recruit osteoblasts at the site where they resorb the tissue, we call that coupling. And solo is okay in this case. And so that's first concept, that you need coupling. In other words, you need the messages to be delivered after the resorption phase so that the repair phase occurs at that site. And the second concept that is, of course, extremely important is quantitative, and we call that balance. In other words, ideally, the amount of bone that is formed here during that phase is equal to the amount of bone that was resorbed during the resorption phase. But of course, there are many, many instances of imbalance, and these imbalances can lead to either bone loss if the resorption is dominant, or bone gain if the formation is dominant. So this is the cyclic activity of remodeling that is happening in millions of microsites in your skeleton as we speak. And the third dimension is time. And this dimension is the activation frequency, which determines the turnover. So basically, it's easy to understand that the more frequently you're going to go through these cycles, the more bone you're going to lose if you're in a negative balance, or the more bone you're going to gain if you are in a positive balance. And as you will see, these concepts are important when we think about treatment. Now, it so happens that these activities of remodeling in the normal adult cover only about 10 to 20% of the surfaces of the interface with the bone marrow. The other 80 to 90% are what we call resting or quiescent surfaces, where the cells are lining the mineralized tissue. Notice always this very intimate relationship with the bone marrow, okay? And they are not active in terms of matrix resorption or matrix deposition. They are active in transport of many things. So these quiescent surfaces, however, can be activated, and in the last 5 years it's been shown that these not very interesting looking cells are actually mesenchymal stem cells that can be activated under the right conditions to form bone, this time directly. And when I say directly, that means independent of the fact that you need a resorption phase before. So this is the mechanism by which the skeleton homeostasis is determined. And we have to add, in addition to the remodeling sequence that I described before, what we call modeling, which means a direct activation of these quiescent cells that can then go for a very long time if needed, and at the end of which it can either go back to quiescence and be the lining cells that we described before, or go through activation of that surface, initiating a remodeling sequence. Okay. So, it's clear that modeling and remodeling are very important because they allow adaptation to local and systemic changes, increase or decrease bone density. They adapt the microstructure to the load that the skeleton is exposed to. They allow storage or mobilization of calcium and phosphate. Of course, they participate to the normal turnover of the tissue, that is to renew bone matrix components, including the osteocytes, right? While maintaining skeletal homeostasis, in other words, bone mass. But things don't go always as predicted, right? And this is an old slide, but this illustrates very nicely that in men and women, as we age, our bone density decreases constantly. You notice that in women, there is this period of about 15 years, perimenopause and postmenopause, during which there is a tremendous acceleration of bone loss. Now, if you started from a lower peak bone mass, which is the bone mass you've acquired at the end of your growth period, let's say, so if you start lower than the standard, you reach a level that we call the fracture threshold, in which now you have so little bone that the microstructure of the tissue is modified compared with normal and does not allow sustaining the normal weight of your body. And that leads to this situation where vertebrae are crushed, usually without any trauma that can be identified. And this is what happens. This is a slide that shows 3 generations of women, apparently in Asia in this case. But you can see what happens with aging, or happened maybe with aging. And it was always considered as normal aging. Well, it is not normal aging. It is osteoporosis. And it affects a tremendous number of people, both men and women, predominantly women, but also men. And why is that a problem? Because at age 50, it is shown that your probability of having a fragility fracture, which we mean it's not a ski accident, right? So you walk or you fall and you break, right? Is of about 25% for men and about 50% for women. So your age 50, the probability that you're going to have such a fracture is 1 in 4 or 1 in 2. So it's significant. Now, again, when we think fracture, we think, well, you know, the 20-year-old on the slopes that break a bone. It's not the same when it is a 75-year-old person, right? And this just to remind you that the morbidity of osteoporotic fractures is very significant. It is not just a fracture in a youngster. about 20, actually currently people think it's more 25% of the people affected die within the year after the fracture, especially hip fractures, okay? And 30% have permanent disability. So it is a significant event. So now we go back to my remodeling cycle and say, how can we prevent or treat this progressive loss of bone with time? And of course, the first thing that comes to mind is, okay, I'm going to block the resorption because it has a negative connotation. Resorption, that's kind of bad. So let's try to block it. And we've been quite successful at doing that with two agents. A monoclonal antibody that blocks key cytokine, rank ligand. This cytokine is required for the differentiation of the cells. And that's called denosumab or Prolia for the people who have heard about that. And the other that I'm sure everybody has heard about is the bisphosphonates. It's an older story, but it continues to be the standard of care, okay? So we have, these two are very efficient, and what they do is essentially they remove the osteoclasts from the scene, okay? And now that you're experts on bone, after bone 101, we can go to bone 102, which is that if you have done that, what do you expect? Well, you expect this, no coupling, therefore decrease in or suppression of bone formation. And it turns out that this is exactly, and also you expect a marked decrease of the turnover of the tissue, okay? And this is exactly what's been observed in all the clinical trials. So in this example, it's a comparison between a bisphosphonate, alendronate, and denosumab, the anti-rank ligand antibody. And you can see that both are very successful at decreasing this bone resorption marker, 60–70% with that, and 90% with denosumab. So very efficient treatments. But after a short period of time, you have a delay because of the remodeling cycle. Now you can see that bone formation in both cases is decreased by 60–70%. The balance between the two is still positive. So the patients are still gaining bone density, especially because of this lag between the two events, okay? But as you can imagine, it is not ideal. And in particular, suppression of the bone turnover leads to a number of issues, including, paradoxically, some fragility fractures. So the field has been looking for a very long time for what we call anabolics or osteoanabolics, where we would not suppress the resorption side of the equation, but increase the bone formation side of the equation, okay? And we have discovered two different pathways. By the way, I'm not showing data from my lab, but trust me that we contributed to many of these little steps in the story. Okay, so one pathway is parathyroid hormone. Parathyroid hormone, when given intermittently, that means one injection a day, as opposed to continuously high, is anabolic. And the other is the story I want to tell you, and that is sclerostin antibodies. Okay. And the reason why I want to tell you at the invitation of Larry is because it's a fantastic example in the history of medicine, I believe, of different groups working on completely different things, very rare, what we call ultra-rare diseases, that opened the field to this major progress. So the first two diseases are one called sclerosis here. And you can see just from this X-ray that these patients have a very high, abnormally high with side effects, etc., bone density. And the other is von Boehem syndrome, which are equivalent but not as pronounced. Now, in both cases, the gene that was causal was identified as a protein that they called, at the time, of course, sclerostin. This one is a null mutation, and this one is a deletion in the promoter, which decreases markedly the level of expression of the protein. Now, what attracted the field and the industry, many companies at the time, was the observation that the haploinsufficient carriers, the heterozygotes, have high bone mass, as shown here with these red dots, compared with the normal range. But they have no side effects because it's a moderate increase in bone density. So, of course, the idea was immediately, wow, if we can mimic that situation, we can have high bone density and maybe no other problems. Now, the same year, and that's the work that I was involved in also, same year, two other groups. One working here on osteoporosis pseudoglioma syndrome, an early onset osteoporotic phenotype, and a group that had identified a family, completely normal family, but on X-rays they showed very high bone density. And both groups we were pursuing genetically to try to understand what genes were altered in this situation. And it turned out, and unbelievably, it's very rare, that the osteoporosis phenotype was a null mutation of this receptor, LRP5, when the high bone mass family was a single mutation in the same receptor. And these papers were published 6 months apart. Okay? And 6 months apart from the other one on sclerostin. And the magic of that series of discoveries, all from ultra-rare diseases, is that it turned out that the single point mutation that led to the high bone mass did not create an autonomously activated receptor. What it did was to decrease the affinity of the receptor for sclerostin. Until then, we did not know what sclerostin was doing. Now we learn, lo and behold, that this is a key regulator of bone mass in human. No mice yet. Okay. So this added, sorry, I should go back 1 second to say that this receptor LRP5, there is another one, LRP6, that has been shown as well after, but is a co-receptor with the Frizzled family of receptor of Wnt signaling, like we heard this morning, right? And this told us that canonical Wnt signaling, the beta-catenin-dependent Wnt signaling, was a key regulator of bone mass in humans. So I don't want to go in all the complexities of the Wnt signaling pathways. We are not here to do that. But just to say that, of course, this called the attention of the entire field on this pathway. And this pathway is characterized by, of course, signal transduction and transcription and so on, but also by a very large family of endogenous inhibitors, because it is a very powerful pathway that is involved in everything developmental, okay, and has many endogenous inhibitors, among which sclerostin. Okay. So the next question was, okay, now we know this pathway is important, sclerostin is important, but where is all of this happening, right? So subsequent work, identified the source of sclerostin as the osteocyte. It's essentially the only source of sclerostin within bone and more or less within the entire organism. So it's very, very interesting. You can see here two osteocytes and their dendrites reacting for sclerostin. So now we know that the source of the sclerostin is the osteocyte. But where is the target? And in this beautiful experiment done by my colleague at Harvard, what they did was to introduce in mice the single point mutations of two of the patients, targeting the mutation to osteocytes only, okay, with the right promoter. And what you can see is a gene dosage dependent in both cases increase in bone density, both trabecular bone and cortical bone, by introducing this single mutation in the receptor in osteocytes. So here we are. It's really intriguing, right? That the whole phenomenon we are observing here is sclerostin made by osteocytes and binding to LRP5 receptors that are also in osteocytes, but also on osteoblasts and also on lining cells. So a very microenvironmental phenomenon. Okay, what I want to say now that it is so microenvironmental that it's key to think a minute about it in order to understand how we develop that. So basically, many studies are involved in what I'm showing you here. And these studies have shown that if you're in a microenvironment, and again, we are talking really bone cells, where the stoichiometry is in favor of the inhibitors, sclerostin and one that I'm not talking about, DKK1. Under these conditions where the Wnt ligands are at low concentration, you have, of course, these inhibitors bind to LRP5, and what they do is sclerostin recruits a co-receptor called LRP4, and DKK1 recruit cremin, but in both cases, the result of this interaction is the internalization of the entire receptor complex. So what they do is actually remove LRP5 and 6 from the cell surface. And when this happens, beta-catenin is degraded in the cells, bone formation decreases, and bone resorption increases. In contrast, if you're in a microenvironment where the stoichiometry is in favor of the Wnt ligands as opposed to the Wnt inhibitors, now it's the Wnt that binds to LRP5, recruits frizzled as a co-receptor. This stabilizes beta-catenin in the cells, increases bone formation, and that's not a small event, also decreases bone resorption. So how is this sclerostin endogenously regulated? Well, very interestingly also, the main regulator we know is mechanical loading. So I told you these cells are the sensors of mechanical loading. And what is shown here in mice is that if you load, the expression of sclerostin, which is high in the unloaded bone, is decreased very markedly. So when you decrease sclerostin, of course, you're going to increase bone formation. Now, based on that, in collaboration with Mary Boxine, that you tried to get but could not today, but she is the PI on this, not me, supported by the NASA, As you know, in space, one of the key issues is lack of gravity, and lack of gravity leads to very rapid loss of bone in space, which is why you see all these people doing this exercise and so on. So what is very fascinating is that since we know that decreasing sclerostin is what happens when you load the skeleton, the idea was if we decrease the sclerostin expression, we are mimicking loading, right? Whoops. I don't know. So this is the mice that stays on ground. This is how they came back after 12 days, massive loss of bone, as you can see. And this is how they came back if they had received one injection of antibodies to sclerostin before takeoff. So, pretty striking. And lo and behold, the second key regulator of sclerostin turns out to be the other anabolic pathway that is being used, that is parathyroid hormone. And I don't need to go through the details, but through cyclic AMP, activation of the receptor by the hormone leads to a suppression of sclerostin expression. It is not the entire mechanism by which PTH works, but it contributes to its activity. All right, so now that we know how it's regulated, we know where it's acting, what are the receptors and so on, how does it work? So we've learned that the Wnt signaling pathway targets progenitor cells, mesenchymal stem cells, or osteoprogenitors, depending where you look at, and increases their proliferation briefly and favors their differentiation in the osteoblast lineage, blocking differentiation in adipocytes and blocking differentiation in chondrocytes, cartilage cells. And when you do that, of course, the end cell of this lineage is the osteocyte. So, of course, the mechanism here is a negative feedback loop, where the end cell, and notice I didn't say terminally differentiated cell. I learned that this morning. Secretes sclerostin locally to tone down this very potent activity of the pathway. And as we said, loading, PTH, and I also mentioned here estrogen, are actually repressing this sclerostin to favor bone formation. So, of course, it was an obvious target for drug development. And several companies developed humanized human monoclonal antibodies to block sclerostin. The idea, of course, was obvious, but what was not obvious was to think about whether the antibodies would be able to reach the site of production of sclerostin, but they do, so we've been lucky. Okay, and the expectation was that if I do that, now I block this negative feedback loop, and I expect that I'm going to favor osteoblast differentiation and bone formation. But we've learned in the meantime that the pathway also increases this cytokine, osteoprotegerine, which blocks bone resorption. So now that's what we expect, an increase in bone formation, a decrease in bone resorption. I'm looking at my watch. Yeah, I'm terrible with that. Okay. Yeah. All right. So, and lo and behold, this is exactly what was observed. The surprise was not the amplitude of the increase in bone density, in bone formation, but the amplitude of the decrease in bone resorption. And the mechanism by which it does that is by activating, and I'm just going to speed things up seriously, quiescent surfaces. Quiescent surfaces are activated directly into bone-forming surfaces. And this leads to this very significant increase in bone density at all sites, much more than parathyroid hormone or bisphosphonates. Okay. Improves the structure, you have to believe me on this. Okay. And decreases the rate of fractures in all the clinical trials. Okay. I'm sorry, my timing is completely off. So I want to just finish with the other rare diseases, 2 minutes. One is that it was discovered another sclerosis phenotype where the mutation is not in the sclerostin itself, but in the receptor LRP4, which is a co-receptor. The other was, and that's from my own lab, that we identified the cause of another very rare disease called pile disease as a null mutation of another inhibitors of the Wnt signaling pathway, SFRP4. And finally, it's been shown that the Wnt signaling pathway is also responsible for some of the osteogenesis imperfecta phenotypes. Okay, so this is what I wanted to illustrate here. That starting from actually 4 different phenotypes here of ultra-rare diseases, we identified 3 more rare diseases that are also on the Wnt signaling pathway. And more importantly, this information has been used to develop a drug that is now on the market. It's called Evenity, that is extremely efficient at increasing bone density. I switched some slides, but we can discuss about that. And when I said in my title, comma, and back, it's because this information is now coming back to rare diseases. And in particular for these antibodies, for osteogenesis imperfecta, there is a phase 3 ongoing with another inhibitor of sclerostin. But I want to also emphasize that 3 very rare diseases have found treatments in the last 5 years, more or less. So, all right, and I want to finish on MCTO because it's another rare disease that we would very much like to understand and treat, where bone is disappearing in children at very rapid rate. And I just want to show this is human, this is the mouse that we are working on that from Dr. Takahashi. And you can see that it mimics pretty closely what is happening in humans. So the quest is to understand the disease and to find a treatment. And Lauren, after me, is going to develop on this thing. Thank you for your attention, and thank you. Sorry for being here.
Thank you for that elegant story about how bone is regulated in our body. It's miraculous that it works well. And thank you for your contributions to making it work better for those who need it. We have only a few minutes for questions. Sorry, go ahead, Meredith.
Can I start with a question from online? Michael Levin says, thank you, Roland. He says, a tour de force. Question is whether inhibiting sclerotonate.
Sclerostin.
Thank you. I'm too tired today. Can decrease chondroblasts and interfere with bone growth.
Can you say that again?
I literally am going cross-eyed here.
Sorry, Meredith.
Oh, shoot. Now I don't have my glasses on. Sorry. Thanks, Roland. Question is whether inhibiting sclerostin can decrease chondroblasts and interfere with bone growth.
Well, that's of course a very good question. We do not know the answer to that. I can say that in the animal studies, at least, because kids have not been treated with this yet. But in animal studies, even in the knockout, there is no change noticeable change in growth. So I doubt that it has a negative impact on chondrocytes and the growth plate.
Thank you.
This could be the dumbest question I've ever asked, but so it's all right.
Doubt it.
So, listening to you, and this is the first time I ever thought about bone marrow, ever, except when I ate it in a restaurant. And it made me wonder, since most of the cells that are in the bone marrow, I think, have not too much to do with bone growth at all. They have more to do with the immune system and God knows what else. Why isn't there in bone-bearing animals a tissue called the bone marrow, except we wouldn't call it the bone marrow, we'd call it something else,
Yeah.
and that makes all those cells and make the bones even stronger without all that weakness in them.
Okay, it's not surprising, but it's not a dumb question, okay, at all. The interaction between the marrow and bone is extremely intimate. That is, it's been shown that if you alter things in bone, it does alter hematopoiesis, one lineage or the other lineage, or the stromal cell mesenchymal proliferation in the marrow, and reciprocally. T cells and B cells do influence bone as well. And so the interactions are both ways and very critical. You cannot develop proper hematopoiesis if you do not home the hematopoietic stem cells inside the bone. In osteopetrosis, where they don't have space to develop within the bone, they develop in the spleen instead, and you have very serious hematological issues.
Unfortunately, I think we have to move on.
Okay.
We
Sorry
can
for
continue that. Thank you, Roland. Our last speaker of the day is going to